Alright, so in Chapter 8, we're going to start looking at the periodic table a little bit differently from how we have in the past. Before, we primarily used the periodic table as a reference tool just to look up things like atomic number or the molar mass. But in this chapter, we're going to see that there's a lot more to the way that the periodic table is organized. Um, Over the years, the periodic table has actually evolved. Of course, when the periodic table was first introduced, all of the elements were not quite well known yet. Some were completely unknown. Some of them haven't even been discovered until a couple years ago, and there will certainly be more in the future. And as we discover more and more elements, the periodic table's organization may or may not change. But you have to remember that there were a lot of empty spaces on the original periodic table. But that's important because the presence of empty spaces on the periodic table is what allowed us to figure out that there were other elements out there. Initially, the periodic table was organized based on just properties of the elements. For example, folks started to notice that there were some repeating patterns within the elements. For example, if you were to take lithium and beryllium and boron, carbon, nitrogen, oxygen, and fluorine, and then neon, okay, these elements right here are listed in terms of increasing molar mass, okay? And what we notice is that as we keep on looking at increasing molar masses, that we start to see a pattern emerging. And I'll show you that pattern here in a second. But after sodium, we have magnesium. And after magnesium, we have aluminum. And then we have silicon, phosphorus, sulfur, chlorine, and then argon. And what's interesting here is if you look at the properties, again, these are all increasing in molar mass, almost all of them. I'll show you in a second. You notice that both lithium and sodium had some similar properties. They're both metallic, shiny, they were soft metals. If you threw them in water, they both went kaboom, a big explosion. They produced hydrogen gas. Okay. And if you looked at beryllium and compared that to magnesium, you saw that there were some similarities too in terms of the fact that they both form similar types of compounds where the metal takes on a +2 charge. Okay, we see the same thing with boron and aluminum. Boron and aluminum are both going to be trivalent. The compounds that they form that are trivalent tend to be very Lewis acidic. So again, a lot of similar properties there. And this continues as we go on down the line here. Carbon has a lot of similarities with silicon. Nitrogen has a lot of similarities with phosphorus. Oxygen has similarities with sulfur. Okay, and then fluorine and chlorine. And then the last one I want to show here is neon and argon. Okay, and you'll notice that the steps are about the same here. So going from lithium to sodium, it's 1, 2, 3, 4, 5, 6, 7, 8 elements. So there was a repeating pattern every 8 elements, which gave rise to this concept of the law of octaves. Okay, but this kind of fell apart once we got to argon. You see, argon has a molar mass that is higher than that of potassium. So if we kept things organized in terms of molar mass, potassium, which is something that explodes when put into water, would wind up in the same group as the noble gases. And argon, which is completely inert, would wind up in the same group as lithium and sodium, which are explosive in water. So that didn't seem to make sense. Okay, so the relative arrangement of potassium and argon indicated that we needed to not organize the periodic table in terms of increasing molar mass, but increasing atomic number. And it turned out that that worked out pretty well for all the elements. And there's actually a couple of different elements that we see moving from left to right on the periodic table. We have an increase in in atomic number, but not the molar mass. Okay, now there was a fellow by the name of Mendeleev, okay, which many people recognize as being the father of the periodic table, or modern periodic table. He did something very important with the periodic table, and that is he found a blank spot, okay, an empty spot right underneath aluminum. And he proposed that there must be some element that fits into that spot there. And what he did was he looked at all the trends on the periodic table, and he started to make predictions about what that element would look like. Okay, so he was able to do things like predict its melting points, density, all sorts of stuff, reactivity. And what he did was he gave a name to this. Okay, he called it Eka aluminum. Okay. Many years later, Eka aluminum was actually discovered. They didn't call it Eka aluminum, they called it gallium. And what was interesting was that Mendeleev's predictions were actually quite accurate. And that's always the thing with science, is if you can put together a model, it's one thing for that model to look organized and to explain things that we've already seen, but it's definitely a whole different ball game when that model can actually predict things that haven't happened yet. And this is what really cemented his place in history. Okay, so in the next videos, we're going to look at some of the particular periodic trends that are graphically represented on the periodic table.